Welcome to the module on the fundamental equation of thermodynamics, where we will be combining the first and second laws of thermodynamics. Up to now, we have looked at the first and second laws of thermodynamics somewhat separately. But when considering a thermodynamic process, both the first and second laws must apply simultaneously. According to the first law, the change in internal energy of a thermodynamic system, du, is equal to the heat exchanged between the system and its surroundings, delta Q, plus the work done on or by the system, delta W. This relationship is also valid for reversible changes. Therefore, du is equal to the sum of the heat exchanged in a reversible change, delta Q rev, plus the work done in this change, delta W rev. According to the definition of entropy, reversibly exchanged heat is equal to the product of current temperature in the system and the differential of entropy ds. For the sake of generalization, we will consider all possible types of work done by or on the system. It consists of the familiar volume work due to expansion or compression of the system and other non-volume work types. Generally, the infinitesimal change of work due to a specific physical interaction can be represented as a product of two quantities. Here they are shown as uppercase x times the differential of lowercase x. These two quantities, uppercase x and lowercase x, are known as conjugate variables. In the pair of conjugate variables, the uppercase x is an intensive variable. It is a generalized force determining the interaction between the system and the surroundings. The lowercase x in the differential represents an intensive property acting as a generalized coordinate. It describes a property of the system that is changing under the influence of the conjugated generalized force. The term generalized refers to a mechanical analogy, where work change equals force times the differential of displacement. For instance, pressure and volume is an example of a generalized force and a generalized coordinate describing work done due to the system expansion or compression. Importantly, the product of a generalized force and coordinate must always have the dimension of work or energy. Classical thermodynamics doesn't typically consider non-volume work. However, the concept of generalized forces and coordinates helps to include other types of interactions of the system with its surroundings. Combining elements presented in the previous slide, we obtain an equation known as the fundamental equation of thermodynamics. This equation consolidates the first and second laws of thermodynamics and reads as follows. The differential of internal energy is equal to the product of temperature and the differential of entropy minus the product of pressure and the differential of volume plus the summation term of xi times dxi, accounting for other types of work done on or by the system. Most importantly, this equation contains only the properties of the system itself and employs only state functions. This is because if we assume a reversible state change, we are not concerned about the values of generalized forces, intensive variables, outside of the system. The external forces are assumed to be equal to the internal forces in the system. This equation also lets us examine thermodynamically how the system interacts with its surroundings in a way other than only by volume changes driven by the pressure differences. Although we had originally used a reversible state change to derive the equation, it is universally applicable. It applies to all changes in a thermodynamic system, reversible or irreversible. For irreversible changes, we consider an equivalent reversible change. This approach is similar to the one used to calculate entropy change. We will further use the fundamental equation of thermodynamics to establish some general thermodynamic relationships. But now I would like to draw your attention to the following fact. Let's look at the term T times ds using an analogy with generalized forces and coordinates. Here, temperature T is an intensive variable. You can think of temperature T as a type of force that controls thermal equilibrium. The entropy S is an extensive variable, and it can be understood as a generalized coordinate conjugate with temperature T. You can think of entropy as a coordinate that the system moves along when heat is transferred due to a temperature difference.